Hello, everyone. Thanks for taking the time to join us today. Today, we'll be talking about high performance computing on AWS and how we can unlock innovation without infrastructure constraints. So, we'll walk through what is the current state of on premises high performance computing infrastructure today and how it's evolved over the last couple of decades, and how the cloud computing and how AWS specifically have helped researchers around the world and scientists and technologists and engineers rethink high performance computing to get significantly improved business outcomes today and into the future. And some of the AWS HPC services that actually enable this significant shift in high performance computing, and we'll close it out with what our customers have actually been able to achieve on AWS with some high performance computing applications. And if you think about high performance computing, although the field itself might seem scientific or academic, it actually touches pretty much every part of our life. To having our cars designed to be most optimal, as well as handling anything from our investment portfolios to even the latest movies that we watch, to the traditional HPC applications we're all familiar with respect to, say, doing things like weather modeling. And fitting to our times that we live in, both preventing the rapid spread of COVID in the early days in 2020 with the several interventions that were put in place by governments, as well as the rapid move to design vaccines and now distribute vaccines to everyone. It touches every single part of our life. Right? And you would think that over the several decades that high performance computing has evolved, it should be fairly easy for researchers and engineers and technologists to take advantage of high performance computing. But the reality is, even today, 2/3 of HPC practitioners report that they have a significant barrier to taking advantage of HPC compute on-prem, where the wait times are either too long. If you're a researcher and you're trying to run a large-scale job, in pretty much any institution, you end up waiting at least several hours, if not several days to weeks, before your jobs can be properly scheduled and run. And one of the ways to think about it is when you're trying to design an on-prem system, you're designing it based on the computing needs that you can forecast today. But every time the compute demand goes up, there is a significant planning process that needs to be added on to the overall system. And when we go into going in and thinking about how you go design these systems, you have a project planning phase, and then there is an implementation phase, which comes with large acquisition costs and acquisition delays. And every time the business scales, there has to be a significant delay. Where ideally what we really want is at any point in time, when you need the compute, we actually get it to the researchers and scientists and engineers at exactly the moment they need it. And this is another way of looking at it, where even if there is an on-prem HPC system that has already been commissioned, the capacity of the HPC system is fixed. So the number of jobs that need to be run, that can be run on the system, have to be in some way, shape, or form managed or organized or bin packed to make sure that you can actually fit it to the data center capacity. Think about it for a second. You are trying to enable scientists and researchers and engineers to get a big business outcome, but instead of fitting the computational infrastructure for the business needs, the researchers end up spending enormous amounts of time to fit the artificial constraints imposed by the fixed infrastructure constraints. So instead of driving to a business outcome, we are driving to a fixed infrastructure constraint. Instead, using HPC in the cloud, we can actually surge to get a surge capacity whenever we need to, and pay for the surge capacity when we exactly need to. But then once we are done, we actually spin it down so that we actually don't pay for infrastructure that is going waste. In the fixed data center capacity mode, there is a constant push to make sure that the infrastructure is actually at a high level of utilization. And if you size it to be too large, then you're always running an infrastructure that actually is running idle most of the time, which is a significant business cost. Or if you size it too low or too small, then you're running into the situation where your surge capacity is never met, and you're always going after suboptimal results that actually are fit for an infrastructure constraint, not necessarily a business constraint. That is a fundamental shift that we're trying to unlock, and we'll walk you through what several businesses have actually achieved by moving to the cloud. Right? And as always, in the Amazonian way, we work backwards from the customer needs. And there are two kinds of customers when it comes to high performance computing, very similar to other kinds of compute as well, where we have the line of business users who are actually asking for functional improvements, things like faster development cycles or tools to improve insights that they get out of the investment they make in running these simulations, both the engineers or scientists or technologists' time as well as the compute time, and easier access to data, right? The flip side of that is the infrastructure question, which is mostly run by the IT teams, where they're worried about what is the overall cost. Are there capabilities where we can actually forecast our costs in a reliable way? Are we secure? Can we actually get to our data in a reliable fashion over the long term? So these are two different kinds of asks which drive to the same business outcome, but need to be met with different solutions or different parts of the same larger solution, which is really what we've done, working backwards from both of these requirements, going in and making sure that our services actually meet both of these requirements. Right? Just to give you an idea of different kinds of workloads that are supported on AWS, there are typically two kinds of high-performance computing workloads. One is called tightly coupled workloads, other is called loosely coupled workloads, right? So as the name suggests, tightly coupled workloads, the ones that are shown on screen now, are workloads where every part of your simulation, or at least most parts of your simulation, needs to communicate with most other parts of the simulation in a regular period, in a regular intervals throughout the simulation. So that means every part of the simulation and the infrastructure needs to be able to communicate with each other as your simulation is progressing. That's where the term tightly coupled comes in, where if we are trying to design, say, for example, a Formula One car shown on the screen with computational fluid dynamics, pretty much every part of that particular simulation domain that we break down to run in individual nodes need to communicate with each other to solve the entire solution. Whether it is solving the reservoir simulation example, in this case it's shown from Halliburton, where they're trying to maximize the extraction of natural resources from a particular reservoir, and they need to figure out what are the optimal locations where they can actually go in and extract the oil and gas available. To do that, every part of the system actually needs to communicate with each other, right? And same goes true for weather modeling as well, where if you're trying to predict weather over the entire continental United States, you need to be able to predict what is going to happen across the entire domain of the solution. And the entire domain of the solution depends on each other. So that's the tightly coupled workload nature of the situation. And all of these are run on AWS today. The other end of the spectrum are the loosely coupled workloads, where the individual parts of the simulation don't necessarily need to communicate with each other throughout the simulation. Each of them can work independent of each other. And this kind of simulation is sometimes called embarrassingly parallel, where you can pretty much run all of these simulations completely independent of each other. But the difference is, the example would be, say, a bank or a financial institution running financial risk calculations. So they need to run through hundreds of thousands, if not millions of scenarios to figure out what is the risk of a particular portfolio. So to get there, each scenario they're running might be independent, but the job scheduling, making sure that all of these things are run in a reasonable period of time, and the results of the simulations can then be aggregated back out after the simulations are done, need to be managed effectively. That's a loosely coupled portion of the high-performance computing portfolio. And both of these simulations are run today on AWS, and we'll walk through some of the examples of companies doing it successfully at the close. But before we get there, we wanted to walk you through what key services that we have that enable high-performance computing on AWS. Right? So out of the 200 plus services we have, these are the key services that support pretty much all of the high-performance computing workloads, in addition to the overall networking layer that we have in place, right? So we will talk about each of these services in a little bit more detail as we go through the presentation today. But to give you an introduction, so AWS Parallel Cluster is our solution to spinning up clusters in a programmatic fashion and making sure that the clusters can be managed by the HPC practitioners without necessarily having to go through the burden of making sure that all of the underlying mechanisms to manage a cluster actually need to be taken care of, right? And of course, we have Amazon EC2 instances, and there are specific instances that we'll highlight today, but just the sheer combination of instance types, networking, and storage that go with those instances makes us the broadest and deepest portfolio of instances available anywhere in the cloud, right? And we have our own Elastic Fabric adapter, which enables up to 400 gigs of networking across instances that actually is designed for tightly coupled workloads. We have FSx for Lustre, which is a distributed file system based off of the open source, widely used Lustre file system that enables significantly large IOPS over very large scale distributed compute nodes. In a seamless fashion, we'll talk you through what are the advantages of using FSx on Lustre on AWS. And of course, we have AWS Batch, which is a cloud native scheduler that runs containerized workloads across very, very large scale workloads that are being run by customers today. And running HPC workloads has never been easier on AWS and on any cloud with these services combined together. Right? So we'll start with Parallel Cluster. So Parallel Cluster it simplifies the deployment of clusters on AWS. So everything from the cluster management tools to schedulers to the auto scaling groups are automatically taken care of for our customers. And you can run both tightly coupled workloads as well as loosely coupled workloads with combination of Parallel Cluster and Batch together using Parallel Cluster, right? And one thing to note is Parallel Cluster is the first solution to be approved as an Intel Select solution, which Intel signifies as a solution that actually combines compute, networking, and storage in a way that optimizes the deployment of high-performance computing systems to our customers. And Parallel Cluster comes natively with support for all of our HPC services. So EFA that we talked about, FSx for Lustre, all the instance types, as well as AWS Batch. And going to the next level of detail of how our customers would use Parallel Cluster, the customers would connect or spin up Parallel Cluster through, say, a CloudFormation template. But what Parallel Cluster does is it automatically takes care of the VPC creation. If you need to create a VPC, or if there's already an existing VPC, it can create the master node shown in the middle, which is the primary server in your VPC, along with an NFS share attached to it, backed by S3. And it automatically spins up an auto-scaling group. And the advantage of Parallel Cluster today is it supports multiple queues with different instance types in each queue. So what that allows for is a high-performance computing workflow where different teams actually need different kinds of infrastructure to run their analysis and simulations, and they can all be managed through the same Parallel Cluster infrastructure, right? Where think of, say, an aircraft design problem, where you go from an aerodynamics team to a loads team to a structures team to a controls team to a reliability team. Each of these teams would be running their own set of simulations with their own set of software and their own set of architecture infrastructure requirements. And each of them can actually run their queues independent of each other, but actually have a common data system supported by Parallel Cluster to be able to share and collaborate as the simulations are progressing. That's a significant shift compared to how some of these teams operate today. Okay. And if you go into the instance types, there are, as I mentioned, over 400 different instances. but we would specifically like to highlight three of our most recent instances. What we would call our workhorse for high-performance computing for instance types is really our C5N instance, which is an Intel Skylake-based instance with EFA enabled automatically. So we can go in, and when you spin up the C5N instance types, you can actually enable EFA through just a flag. And as long as your codes actually take advantage of standard MPI libraries like libfabric, EFA will work automatically with no code changes required from the customer. Right? And with EFA on C5N, we can get up to 100 gigs of networking bandwidth across instances. The P4D instances are our latest accelerator instances, which are based on NVIDIA's A100 GPU. And that comes, those instances come with 4 EFA network interfaces that allows us to go up to 400 gigs of network bandwidth on the P4D instances. I'll walk through the advantages of P4D, the way they're deployed in ultra clusters, and specifically for machine learning workloads that are optimized for P4D. And our latest instances, which are based off of our ARM-based instances of the second generation Graviton instances, that is the C6GN, an advantage that C6GN brings, where it's an EFA-enabled Graviton-based instance for specific HPC applications, and how customers are already taking advantage of the instance types. Okay. And we've talked about EFA a little bit, but really what enables EFA is our Gen 4 Nitro systems, which is a combination of our Nitro card hardware with the secure software that we run on it, where we've gotten the tax of running a hypervisor to a near zero, where by moving the compute required to do the management of the hypervisor systems off of the actual instance and moving it to a separate Nitro card, we made sure that both the instances can be deployed quickly, as well as making sure that we are reducing the overhead required to run any of our instance types. Right? And our networking, combined with our choice of instance types, along with the choice of our compute and storage, really makes us the broadest and deepest platform of choice. It just gives us a tremendous depth, all the way from going from just 1 gig interconnect speeds all the way down to 400 gigs, and having the capability to size and choose the compute infrastructure for the specific computing needs of a workload completely can change the way our customers think about how they go to market with their high performance computing workloads. Okay, so diving a little deeper on our C5N instances, as I mentioned, we do have EFA enabled in C5N, where we have up to 100 gigs of network bandwidth, and you can get a significant bandwidth where you're going in and it has a custom designed Nitro chip that actually enables you to go run tightly coupled workloads efficiently. And I'll walk through some examples of customers who've taken advantage using C5Ns. I mentioned P4Ds, where P4Ds are best-in-class accelerated computing instances with NVIDIA's latest Ampere-based A100 GPUs. And the P4D instances come with 8 A100 GPUs. Coupled with our EFA, we get 400 gigs of network bandwidth across these clusters. And the interesting way we've designed the P4D instances is each of these instances are not only optimized, but they're all optimized in what we call an ultra cluster in terms of deployment, where all of these instances, over 400 individual P4D instances, actually are deployed in an ultra cluster sitting in the same network spine. What that enables us to do is actually get us to a supercomputing class cluster, where if you wanted to have a workload that runs across all of these instances with several thousand GPUs working together, for example, a natural language process model like a GPT-3 model being trained on, say, several thousand GPUs can be done in one of our Ultra clusters. And several of our customers are already taking advantage of it. This also accelerates several other HPC workloads, like which can take advantage of GPUs, like some CFD workloads that actually are GPU enabled. And we're seeing a significant increase in interest from our customers wanting to use more accelerator-based instances for GPU as well. And just a tidbit of information here, if you look at the top 10 supercomputers in the world, out of the top 10 supercomputers in the world, more than 80% of them actually are GPU-based supercomputers today. And we are seeing a definite movement towards supercomputers being enabled through large-scale GPUs moving forward into the future as well. So here is an example of a CFD simulation with 24 million cells trying to predict what would be the effect of flow in a very complex body. And it was run up to 1,200 cores. Now you can see without EFA enabled, and comparing that to an EFA enabled thing, that's the purple versus the blue lines, up to about 300 to 400 instances, the performance is more or less comparable because you've not hit the communication barriers yet where the losses are not large enough to add up. But once we cross the threshold of about 400 cores, you can start seeing a plateauing of the instances where the EFA is not enabled. And then crossing about 600 or 650 cores, there's a rapid decline in performance, which means that you're adding more nodes and getting poorer performance. In fact, you get to about the same performance with 1,200 cores as what you got with 200 cores, which is a significant waste, right? That's because the communication losses, so the latencies introduced because of the communication losses, completely overwhelm any gains you're achieving by increasing the compute power. Compare that to EFA, the performance gains continue to increase near linearly, and you're getting efficiencies or parallel efficiencies to scale well beyond 75%, right? Where the perfect scaling, where if we had no losses, is shown on the red line, that's the 45-degree line. And EFA comes as close to that line as possible, right? So that's a significant boost. And this is a test that we ran. But what was even more heartwarming is actually to see this result from the Naval Research Lab, where the US Navy, without any help from us, actually tried scaling their own simulations on multiple systems. So they used several of our competing systems on-prem as well as us. And even on AWS, they used an instance that was before a previous generation instance, C4, and compared that to C5N. And when C4 was there, we hadn't yet introduced EFA. And after the introduction of EFA with C5N, they compared both of it. And the way to read this chart is the lower the number on the x-axis, the better. Meaning the time on the y-axis is better, meaning the time to compute something being slower means you get the best answer. And you can see very clearly C5N beats every other system handily. And more importantly, as you reduce the number of parallel tasks, you can see that the performance gains achieved by EFA actually holds across the entire board. So there's no crossing of the red curve back into any of the other curves, suggesting that there is a break-even point where EFA performs better or worse. It actually performs consistently better across the entire test range that US Naval Research ran on their own. So this was a fantastic result for us to see, and is also a validation of the way we've implemented both our instances as well as our networking layers and optimized it for large-scale, tightly coupled workloads. Now, switching to storage. So FSx for Lustre was introduced primarily to support large-scale distributed compute jobs that require access to very large-scale file systems with large throughput. And typically what happens is when you increase your file sizes and your file system size, your throughput drops. The advantage of Lustre actually is that the throughput and the performance scales near linearly with storage capacity. So as seen on this graph, as you go from 10 gigs to 10 terabytes, to 1000 terabytes, as you keep adding more storage capacity, the performance or the throughput that you get from that storage actually increases near linearly. So which means that if you go from 10 terabytes to 500 terabytes, your actual throughput goes from 2 gigs per second to 100 gigs per second, which means that you can process more IOPS as you add more compute capability. And that's really the power of using a distributed file system like FSx for Lustre for both tightly coupled workloads as well as loosely coupled workloads. Right? And customers have used FSx very efficiently, both for moving their workloads completely to the cloud, as well as having a hybrid architecture of having part of their workloads run on-prem and part of their workloads run on the cloud only for burst mode. So it's a combination that Lustre actually supports. And now with the latest features, Lustre file system can actually be resized on demand as the file system is actually being used as well. That's a significant advantage. Now, going to batch, AWS Batch is a cloud-native orchestrator where you can have multiple job queues backed by different compute environments per queue, and you can have a large-scale distributed container-based workloads running on batch, where batch takes care of both the scheduling and automatic scaling up and scaling down of the compute infrastructure. Right? So for example, Mobileye, which is a leading provider of autonomous vehicle systems as well as autonomous driving assisted systems, runs consistently anywhere from 200 to 300,000 cores on Spot-backed instances on AWS Batch daily. Right? And AWS Batch also supports Fargate, which makes batch computing completely serverless, meaning users can just submit a job, mention how many CPUs they would like, and batch takes care of provisioning, making sure that the auto-scaling happens automatically, and then users don't have to worry about actually managing the compute infrastructure behind or even worrying about what kind of compute it runs on, right? And if there is like what this slide shows is batch actually you can have two queues, one backed by Fargate and another backed by Fargate on Spot, so that users can take advantage of the cost advantages that Spot gives, as well as be able to scale up and down as needed. So you can set different priority levels for different queues, and if Spot fails or if there's not enough Spot capacity, then you can fail over back to say an on-demand environment and run your jobs. There's no interruption, and you're optimizing both cost and reducing runtimes using batch. Right. Now, HPC workloads are being run across multiple industries on AWS, starting from drug discovery and genomics with Fred and Hutch, or doing financial risk simulations with Fannie Mae, doing exploration and design analysis with Autodesk, or doing next generation weather predictions using Maxar, or doing traditional computer-aided design and computational fluid dynamics based modeling with, for example, F1. And I wanted to walk through some specific examples where customers have shown significant improvement by moving to the cloud. And the Formula One management team is a classic case study where the Formula One management team wanted to give a standard car design to all of the different racing teams to make sure that they're maximizing efficiency and leveling the playing field as a starting point. Unfortunately, they didn't really have access to the level of wind tunnel testing required to go and design a completely new car. They would have required anywhere from 12 to 24 months of locking up large-scale wind tunnels, which they didn't have access to. So the only recourse was doing computational fluid dynamics. But there was also a significant challenge of doing computational fluid dynamics because each of those runs would take upwards of 60 hours that would run on their on-prem systems because they were capacity limited. So they turned to AWS, and moved their workloads onto AWS and actually had a 6-fold improvement in runtime. So they went from taking more than 60 hours to run a simulation to under 10 hours for each simulation. They ran it on 192 cores to upwards of 1400 cores with C5 and 18X large, driven by all of the AWS products that we just walked through, where they're using parallel cluster predominantly to spin up the cluster, and they're doing both on-demand as well as spot jobs for smaller jobs to explore different types of instance types, right? And as Pat Simmons, the Chief Technical Officer of the Formula One management team, put it, this completely revolutionized how they thought about going about designing the next generation of the Formula One experience, where they wanted the sport to be the most exhilarating experience anywhere. And this is something that's near and dear to our heart in enabling them to achieve that. Right? And we don't do this alone. We, of course, are partnering with the most trusted names in the high-performance computing space across the globe, be it our technology partners like Siemens, who both build their technology platforms and run their technology platforms on AWS, to working with our partners like Ansys and Dassault Systems, where it's about bringing the simulation capabilities that are running in any high-performance computing infrastructure on-prem to be cloud native on AWS, to simulation as a service providers like Rescale, or niche providers who actually enable our customers to move to the cloud quickly, like Cloud9 or like 6nines or Ronin, where they're tackling different parts of the HPC community, be it the academic community with Ronin or with large-scale enterprises like 6nines. So what I'd like to leave you with is really go and challenge our customers and your customers with a simple question of what business problems would they solve if they did not have the constraints of compute or storage or the large-scale procurement times, or bound by the costs associated with doing any of these large-scale runs. What kind of scientific questions would they actually be willing to ask if they no longer have to worry about waiting to go run any of these simulations, or if they don't have to worry about the scale, they get the scale when they absolutely need it, and then the scale goes away? What problems would they actually solve? And we're already seeing significantly improved results for several customers unshackling themselves from traditional infrastructure requirements to run high-performance computing workloads. I'll also leave you with the thought that this is just the beginning, to make sure that we introduce you to various high-performance computing services and customer use cases that are already successful on AWS. There's several other training and certification avenues and resources available for all of us to take advantage of, so please take advantage of that. Thank you for listening, and I'd like to definitely invite you to please take the survey for the session so that we can continually improve. Thank you.